to the PTU of Braunschweig. I don't know if I'm saying it right, but thanks for the invitation. It's an honor to talk to you. Hopefully it will be something useful and fun to learn about. Yes, so I try to enter this presentation. You can interrupt if you want, no problems at all for me. And again, it's an honor. I'm here now at Federal University of Santa Maria, and this is what we are going to talk about today. I'll talk a little about our end of the world here, the university, and our course. I also teach at postgrad level here, master's and doctoral. And I'll talk a bit sound absorption today. So mainly giving an overview of sound absorbers, how they behave, and or the absorption mechanisms and methods to characterize those absorbers, such as standardized methods such as the Reverberant Room and Impedance Tube, and in-situ methods that is my my specialty. The things that I did in research most of the time had to do with in-situ impedance measurement, and now we are moving also towards scattering as well. So Gilles studied here. He was in fact advised by me in his diploma thesis. So what is our corner of the world here? So Brazil is a very, very large country. I was born here in the south of the state of Minas Gerais, which you can visit and eat nice food if you want. Anytime, people are very friendly there. But I am now working 1,500 kilometers south of that, in the last state of Brazil before Uruguay here below us, in Argentina here on the side. So Santa Maria is a city, about 200,000 people. There are lots of universities in the area, and we are right in the middle of the last state of Brazil, Rio Grande do Sul. I like this form of presentation where I try to compare some numbers of Brazil and the country I'm presenting to. Now it's Germany, and as we are in an acoustics seminar, I think it's useful to present the information in decibels because it's easier to understand. So in terms of area, Brazil is about 14 decibels larger than Germany, and in terms of population, 4 decibels larger. And in terms of GDP per capita, minus 7.5 dB, low in terms of ranking at least. And in terms of inequality, I always like to put this number here that is not a number, because for sure, if you're working in research in acoustics, you'll come across not a number anytime soon, unfortunately, but you get around it, don't worry. Our university here is located in a very nice, beautiful, sunny campus. It's a nice place to be. Fortunately now the circulation is restricted, but usually in normal days it's like a park in the city, so lots of people come in the weekends to visit the campus. There are open activities as well, and we are a federal university, which means the federal government of Brazil is responsible for maintaining the university, so to speak. And we are about 26,000 students in all levels, like in grad and postgrad, and about 260 courses in undergrad and post-graduation as well. So I think in graduation is about 160 of undergraduation courses. We are about 2,000 professors in all career levels, mean entry levels, and associate professors and senior professors. And recently there was a ranking of Brazilian universities, and our university are in the top 2.5% universities in Brazil. here we have the first and only acoustical engineering undergrad program in Brazil, where Gil obtained his first diploma, university diploma. And about 25%, Gil included, of our former students are working abroad in companies or and in research and development and doing PhDs and so on. And in Brazil, I think most of our market is directed towards building and construction due to new standards obliging constructions to be to have a certain amount of sound isolation. So that's about an overview of the university and the course. And our acoustical engineering program is the only one in Brazil at this point. And in Brazil we have a different arrangement in engineering undergrad programs. We take 5 years to become an engineer in Brazil. And in our course, the last half of the course is all about acoustics and vibration. In the last half, we would see subjects that take a semester like this ones, like room acoustics, electroacoustics, signal processing, digital signal processing, environmental acoustics, psychoacoustics, and so on, numerical methods. So this is for the last half of the course, and students would get really involved in all areas of acoustics. So it's a very large and broad overview of the field. And we are about 5 to 7 professors dedicated. I say 5 to 7 because we currently are 5, but we expect to have 2 more additions soon. So we have to take care of this last half of the course, research and other bureaucratic course duties as well. And of course, in the end, of course, the student has to take a bachelor thesis that takes about 2 or 3 semesters, depending on the student and the project. Social inequality in Brazil is still a major challenge here, and this means that some figures just so you understand what I'm talking about. And 2019 was the first year in our history, more than our history, 520 years after the Portuguese came to our shores. In 2019 was this first year with the majority of Black people attending and enrolled in public universities. So we are a very diverse population, and that was the first year that this less rich part of society is attending now the public universities. So it balances the scale for us around the year, which I think personally is a very good thing. Many students come from a background where speaking English is not a given. So producing literature and reading technical reading material is part of our job. At least we understand that way. And therefore, I took the job to write a book on one of the subjects that I teach here, that is room acoustics. So the book was published in 2016. It has about 650 pages. It's a very large book. Give a lot of trouble to write. And there are 2 chapters on sound absorbers and diffusers, which is the topic of today's lecture. So the book is in Portuguese, so anyone willing to learn Portuguese would have the book and try some acoustics with it. Not the kind of literature to have fun, though. But anyway, we can enter now sound absorption, and I want to give some generalities because I think it's useful for everyone. And so first, we can talk about the mechanisms of sound absorption. So we have basically 2 types of 2 large groups of absorbers. One is the porous absorber, which you see in the figure here. It's a rock wool foam. It's made of fibers that are interconnected. It's very common to use this in soundproofing and thermal proofing of the houses in Europe, I guess. And here on the left, we have a microscope photograph of a phone sample. I think it's in this case, it's a metallic sample. This photo comes from my colleague Paulo Maresi. His PhD, he worked with this. And you can see a series of cavities that are interconnected. You can see only the surface, of course, but you can see the holes here. And the holes in the porous material are very tiny. And sound will enter the material and propagate through the material through these tiny pores. And losses in acoustical energy occur due to the viscosity of the fluids, boundary layers, and so on, and thermal conduction between the air and the skeleton of the material, and also sometimes, but to a lesser degree, skeleton vibration of the material. Usually, we model this kind of porous material as an equivalent fluid. That means that we try to model the sound speed and the characteristic density of the material as a complex and frequency dependent number. So sound speed and fluid density would vary with frequency and be also complex, and that accounts for the losses inside the material. On the other hand, we have another class of absorbers that are resonant absorbers. Usually, in this case, we have a system that is multi-layered. So you would have, for instance, in the membrane absorber, you would have a porous material inside a cavity, and on top of the cavity you would have a flexible membrane that vibrates in consonance with the sound wave. Or you have an example of a photograph here of a corner absorber, so you can apply this to a corner of the room, for instance, to kill low frequency, usually. And here on the right, we have a perforated plates, and on the bottom here, we have perforated plates photographing applied in a room. Here, usually you have the cavity as well, and a gap of air, porous material, and the perforated plates, and sound will enter and be forced through the perforations and enter the acoustical porous material here, and then suffer losses. So this means that usually we have a system that can be characterized as a mass over spring, and then you have a resonance, which is the peak of absorption of those materials. So I have a figure coming with the typical behavior in terms of absorption. So that means that kind of resonant absorbs this multi-layered system, so to speak. Where can we find absorbers? Well, they're everywhere in industry and applications. For instance, here we have in a studio, a vocal booth, singer singing, and lots of porous material here. We can have in the studio other kinds of absorbers, such as the membrane absorber to dump low frequency content. In aircraft, for instance, around the turbine of the aircraft, we have generally a liner here that is composed of a perforated plate and a structure as in a honeycomb structure. So we have a resonant absorber that helps absorbing some of the sound, and of course the phenomenon here is much more complicated because we have airflow and very high levels of sound pressure, so it's highly nonlinear and so on. And even in roads, I guess this in Europe is much more widespread, the use of porous asphalt. It helps with water flowing, so you won't have that film of water on the asphalt, and also helps with sound absorption as well. So sound absorbers are used everywhere, from aircraft, room acoustics. We need the characteristics of the absorbers to actually model the sound field inside the room. And of course, the characterization of those materials is very important for better design and quality control and so on. So our acoustical design of spaces where we spend most of our times in our lives, in restaurants, schools, inside transportation, in our homes. The characterization of those materials is important to assure that we have good design and, of course, better quality of life. And we have standardized and non-standardized measurement methods, and both of them still need further research. We'll see how this is true. And on the non-standardized methods, there are many in-situ measurement techniques. That means we take the measurement setup to the place where the sample is installed. So here is myself back in 2008, when my hair was much darker, working at Microflowne Technologies in Holland and measuring inside a car, for instance. And those in-situ methods can provide us new information and new application and insight about the behavior of absorbers. So here's a scheme of a porous absorber, for instance, a layer of a porous material above a rigid surface, and typically would have a sound wave coming. Here's a very simple model of a plane wave coming in oblique incidence, so at an incidence angle. And conceptually, we usually measure the sound field above the absorber with microphones, for instance, or pressure velocity probes. And then we compute the absorption characteristics. And here are three quantities that are interrelated and help model sound absorption. The first and most intuitive one is the absorption coefficient, which is the ratio between absorbed and incident power in our sample. So it will be a quantity, a real quantity, varying from 0 to 1. And the second quantity is the reflection coefficient. It looks very similar to the absorption coefficient, but it's the ratio between the complex amplitude of sound pressure that is reflected by the complex amplitude of sound pressure that is incident. So in this figure here, it would be the B0 over A0. So you have the complex amplitude of the reflected and the complex amplitude of the incident sound wave. And as this is typically taken from Fourier spectrum of time series of signal, then you have a complex quantity. So typically the reflection coefficient is a complex quantity. It has a real and imaginary part, or magnitude and phase. And if you have the modulus of the reflection coefficient, then you have a quantity that varies between 0 and 1. And the absorption coefficient is related to the modulus of the reflection coefficient by this equation here. And finally, the third quantity that's very important is surface impedance. Here we have the surface impedance that is measured as a ratio of pressure and particle velocity at the surface of the sample. And the particle velocity, as it is a vector, you have to measure it in the normal direction to the surface. So measuring the pressure and particle velocity at the surface of the sample, we can compute the surface impedance. Here's the behavior of typical porous absorber and the typical resonant absorber. I don't mean to be very detailed here, just mean to actually give an insight on how this materials behave. So porous absorbers would have typically an absorption coefficient that increases with frequency, and also it increases with thickness. So the thicker the material is, the more absorption you have in the lower frequency range. But in fact, it's very hard to have high absorption in those very low frequency ranges with porous absorbers. Therefore, we need another solution, and usually we have resonant absorbers, and then we can, for different types of absorbers, we have different behavior, and membrane absorbers tend to work better in the very low frequency range, and perforated plates seem to be working in midway between the very low frequency range and the porous absorbent range. So the thing is, we have an absorption that behaves like this. We have a region or a band of absorption, and then away from that band, the central frequency of absorption, we would have a lower absorption in the lower frequency register and the high frequency register. So regarding these quantities as well, the absorption, reflection, and surface impedance, we want to measure it. So we want to characterize our materials. So we could have such curves experimentally, for instance. And when we are doing an experiment, we would have this kind of behavior where we have a sound source and we have our sample here in gray, and you would have the rest of the floor here or a wall and the room around it. And typically the sound source would emit a sound wave field, and the reflections on the surface of the sample and on the edges of the sample would create a reflected field that we collect with our microphones and sensors. And we rarely measure things directly in acoustics. We don't have direct access to sound absorption, reflection coefficient, and surface impedance. All we have is microphones and pressure velocity probes. Therefore, we need to measure pressure and velocity and use a model of the sound field to compute absorption coefficient, surface impedance, and reflection coefficient. And those models are in the core of our measurement methods. The models can assume a variety of things, and I'm just listing them here. They can assume like the sound field is diffuse, or they can assume that we have a one plane wave, or that we have a spherical wave. We can make assumptions on the sample surface and so on. So usually the more complex the model gets, the more information we can map from what we measure to what we retrieve as a result of absorption of the sample. So we have some standardized methods. So there are standards to cover those methods, and they are very popular. One is the Reverberant Room, and one is the Impedance Tube. They're very well known in our field. So first, the Reverberant Room. We have this ISO standard. It is 354, if I'm not mistaken. And this here in this kind of measurement, the model is assuming a perfectly diffuse sound field, and that means that the energy density is uniformly distributed in space. That's one definition of the diffuse sound field. Or seeing it in another way, it means that energy flow is isotropic, so you would have vectors of intensity coming from all directions in space. And usually this kind of model can be predicted very simply. So how we measure sound absorption in such a context? We have to measure in a very large reverberation room, and you can see a picture of our reverberation room here on the bottom. We turn on a sound source with a broadband sound signal, and you can wait for the sound field to stabilize, and then we can just turn off the sound field, and we can measure the decay of sound, or basically we are measuring the reverberation process. And we have to measure this reverberation process in two conditions, with and without the sample. So we can see a picture here of the empty room, and here a picture of the room with the material that we are characterizing. And if we assume that the sound field is perfectly diffuse, then we can use this sort of nice formula here from very old from Sabine, Wallace Sabine, to map the decay of the sound field and the absorption coefficient. So we can have a map, a direct map between the two quantities. So usually what we are really measuring is the random incidence sound absorption coefficient. It's called in the standard by this alpha with a subscript S, and S comes from statistical because S here can, the alpha S can be seen as an average absorption of overall angles of incidence. So meaning that all angles of incidence around the sample are contributing to the absorption of the sound. This is a widely known method to measure absorption. It's very simple mathematically, and we have extensive databases on many materials measured with those kind of standard. One of the most well-known databases that I know of, at least, is the PTV one in Braunschweig as well. So it's very nice to know that you guys have a very good institute with this kind of measurement there. So what means to measure in two distinct conditions? That means that when we don't have the material, the decay will be much less steep, and when you put the material, there's much more absorption in the room, and then the decay becomes much steeper. And then comparing the two situations, we can compute the absorption coefficient of the sample. So we need this first one to compute the absorption coefficient of the room, and then the second one compute the absorption of the sample. And this curve here is, of course, a bit idealistic. There's no noise. It's a simulation, so just to convey the message. But the method also has some drawbacks. First drawback is that only the statistical absorption coefficient is measured. We can compute impedance and complex reflection factor from this measurement. We need a very large reverberation room, usually. That increases the cost of the measurement. And typically we need large samples are required, for instance, 10 to 12 meters in a 250 cubic meter room. And it is well documented that because of the finiteness of the sample, we have a very large edge diffraction effect that can render indeed absorption coefficients that are greater than 1, which is physically impossible, of course. And there are some recent studies attributing also deviations in the reverberation room measurement method due to non-idealistic diffuse field conditions. So we have this works from Melanie Nolan at DTU and Jamila Balint in Austria that have this, especially when we put the sample in the room, we can see that the decay is not perfectly exponential. Here I know it's linear, but this is in dB scale. So in a perfectly diffuse sound field, that would be a perfectly linear curve and the decay exponential, therefore. But in a non-idealistic diffuse field, this decay will have a double slope decay and therefore deviate from the behavior that the model predicts. And also, we have recently a large interlab comparison published in Acta Acústica, and sometimes samples can have a very large uncertainty. So measurements of the same sample across labs have very different results, which is not good for a standardized method. So it needs further work and research. The second standardized method is the impedance tube. So in the impedance tube, we have a simpler setting, maybe. We have a loudspeaker in one end of a closed tube. And at the other end, we have the material, and we emit the sound source will excite the tube with a broadband signal again, and we can assume that we have under a cutoff frequency that we have plane wave sound field. So we have one incoming plane wave and an outgoing plane wave of the material. So by measuring two positions with two microphones, and by measuring the transfer function between those two microphones, we can compute the sound absorption, surface impedance, and reflection coefficient. So what is really measured is the sound absorption at normal incidence, because we cannot excite the sample in other directions other than normal 0 degree, but we can compute the absorption, the reflection factor, and the surface impedance of the sample at normal incidence, 0 degree incidence. It is also widely known method, standardized, mathematically simple, and it's somewhat portable. A good tube can fit a table, so we have a good, nice bench to work with, and we don't need a very fancy, large room to measure samples. The drawbacks is that the quantities are measured only under normal incidence. It is a destructive method, so we have to cut the sample and put into the tube. There is also evidence of high uncertainty interlab uncertainty. This was published earlier of a round robin between the labs around the world, and sometimes deviations could get to 20 something percent. It also depends on the sample, so some samples are easier to measure than others. And we have a nice experiment that we did here for a project we had with the Brazilian aircraft company, that was to measure several samples. So we got this different kinds of materials, and we cut several samples. And one experiment that we did is to use a single sample and then mount in the tube, measure, take it out, and then mount again and measure the same sample, same exact sample. We did this several times, and we observed that we have a distribution of measurement here. So typically we don't have always the same result, and this result is for a well-behaved sample, but for other fibrous samples we can have like a very large deviation, simply mounting and dismounting the sample from the tube. The same person doing the experiment the same day, and so on. So it's sensitive to the way we mount. So therefore, measuring one sample of one material is not a good idea, not a good approach. And it's hard to measure as well samples with surface variations, or very large samples that can have like metamaterials that the geometry of the sample varies along the surface. You would typically have to choose which part to measure, so to speak. So we can now enter this realm of in-situ methods. That's the main core of, I guess, of today's presentation. But I'd like to give this overview, and I discussed this with Gil as well, that it would be useful. So in-situ methods, we have some sort of perspective of the measurement methods, and talk about a little bit of recent research that I've been developing with DTU and the Technical University of Denmark on microphone arrays, using arrays of microphones to measure this quantity, and also show some results from our study, and so on. So in-situ means that we are taking the measurement set up to the sample. So we take the measurement on site. There is, with the many in-situ methods that exist, and I published in a review paper in 2015 about this, covering a very large ways to measure in-situ. But typically with many of those methods, you would have ways to go around the angle dependency. So we can measure, in fact, impedance and absorption with the dependence of the angle of incidence and frequency. And one can see a trend of increasing mathematical and procedural complexity since the 1950s, when these methods started. So we can see that there are models that consider only plane waves. There are models that consider spherical waves, there are iterative models and methods to retrieve the absorption and impedance. And recently, there's been an attention on the use of microphone arrays to measure such quantities. And we will see why. So basically, the idea from time separation techniques, this is a big class of in-situ methods. The idea is that we will take our apparatus that is composed by a loudspeaker and one microphone near a sample in a room, for instance, and then we would have the direct sound from the loudspeaker to the microphone and the reflection of the sample to the microphone. So we have this pathway 2 that the sound will go into the material and reflect to the microphone, and then we have in the room spurious reflections that do not come from the sample but come from the room, and therefore they are undesirable in that measurement scenario. So we would have an incident reflected from the material, and we need those two somehow, but we don't need the spurious reflection. So if we compute the impulse response in this sort of setting and also compute an impulse response with the loudspeaker and microphone in free field, where we wouldn't have the room around it, then in the second setting, we would only have the incident, and then we can subtract the incident and the free field. And then if we subtract this measurement scenario here from the free field, then we subtract the incident from the signal, and then we end up with the reflected from the material and the spurious reflection. And then we can simply window this, and then we would have the incident and reflected separated in time domain. There are underlying this measurement method is plane wave assumption, and we can have some limited correction for spherical wave incidence, but it's somewhat limited. And we have difficulties at the low frequency range, because the low frequency content of the incident and reflected would tend to mix up with the spurious reflections. Then when we window, we are actually discarding important information in the low frequency range. On the other hand, we have this sound field models as well. That this is another way of measuring the absorption in situ. Usually we have a setting with a loudspeaker and 2 microphones instead of 1, or a pressure velocity probe that mimics 2 microphones and measures essentially the pressure and particle velocity at the same position. But again, we are measuring 2 signals. Here we have this original source, and we have in the model an image source, but this image source here is just for modeling perspective. So in the real scenario, we would have the sound source in the 2 microphones and the surface that you were measuring lying on the ground, for instance, or at the wall of a room. And we can see also a trend of complexity shifting from plane wave assumption in 1985 and this work of Allard and Sieben. In this case, they had to put the sound source very far away from the sample, which actually increases effects of the fact that the sample is finite. And we have a tendency also of making the sound source come closer and closer to the sample. So there is this proposal in 1997, from Lee and Hodgson using 2 microphones. Here they model the sound field as a spherical wave incidence, but only with a simplified specular reflection. And then as years progressed, there's been the use of full reflection models that maps the sound field as a spherical wave, but then try to model the reflection in a more complex fashion. So you would end up with an integral equation that is hard to invert analytically. But it's useful, this kind of model, because then we can use portable devices such as this microphone impedance setup here. So you would have here typically the sound source and the receiver at 30 centimeters distance. So it's very in close range. The device is portable. It can be carried out like in the photographing myself in the car. But usually this means that this model here with the integral equation is very important. And then you need an interactive model to retrieve quantities such as surface impedance, reflection coefficient, and absorption coefficient. So it cannot be inverted analytically, so it's mathematically more complex. The sound field model can also have some restrictive assumptions. So typically, we would have to assume something about this complex reflection coefficient inside the integral, which means that we are assuming that the sample can be locally reactive, or in other words, have a large refraction index, or be infinite in extent. So these assumptions can lead to deviations when you do experiments. So I have these two results here that show effects of edge diffraction. So typically we are measuring a small sample, a finite sample. And when we were measuring this kind of finite sample, what we typically observe in numerical experiments and the real experiments is that the absorption coefficient that is retrieved has these oscillations here that you see in this figure in the middle. And that gets more and more serious and more exaggerated effect when the sample gets smaller and smaller. So this is a 60 by 60 centimeter sample, so it's relatively not so large and not so small, but if the samples get smaller, then this effect gets really, really serious, and you would have a very unuseful absorption coefficient curve. And when you assume that the sample is locally reactive, but the sample has a low refraction index, a low flow resistivity, you typically end up overestimating the absorption coefficient, which we also observe in modeling and in experimental data. We also have a student working here developing an interesting in-situ method that is very easy to use and portable. Here the idea is to actually just bring the two microphones close to the sample and then excite the room in which the sample is and compute the transfer function between the microphones and calculate somehow the absorption coefficient. So this idea was proposed by originally by Takahashi Otsuru and Tomiko in 2005. It's a very simple and insightful method to use. You can even measure with the ambient noise instead of exciting the room with a loudspeaker. You can measure close to the sample and under a somewhat diffuse field. That's what is assumed, but the model that is used to retrieve the surface impedance typically uses a normal incidence assumption. So there is a bit of, we are not sure yet how to compute this for a full diffuse field. We don't have a ready model. But in fact, when we compare absorption coefficients measured in green here, in green is the ISO standard, and in gray is measured with in-situ methods. You can see that agreement for a sample, photo sample, is very good. But again, it needs further research. And with this method, we can measure surface impedance as well. But again, we are assuming something in the model that is not completely clear. And here is a measurement and a model of a resonant absorber. So it's very nice that the measurement does characterize the material quite well. There are some deviations here, of course, because the model is very idealized. And finally, I can talk a little bit about measuring with microphone arrays. So here, the scene that we are typically using is that we have a sound source in red here, represented in red in this scheme. We have a sample that is in yellow on the floor, and we have an array of sensors that are distributed in the space. And this is part of a research project that was started in 2020 in cooperation with the Acoustic Technology Group at TTU, Technical University of Denmark. I'm working in partnership with Professor Efren Fernandez. The idea here is that we are using the spatial information that the microphones, the array of microphones would give us to decompose the sound field in a set of plane waves. So we can find which is the complex amplitude of the waves coming in all sorts of directions in the sample. The method itself was originally proposed by Tamura in 1990s, but it was based on spatial Fourier transform, which has limitations associated with periodicity of the signal that is being measured, and therefore we need a very large sort of sample to measure using the approach proposed by Tamura. And it is limited to regular double layer arrays of microphones, which you see in the figure here. But we are taking a slightly different approach. We are considering this array of M receivers as in the figure, and we have a vector of pressures, sound pressures for each frequency at each of the receivers. And then our model of the sound field is composed of L plane waves. So we have propagating plane waves that are represented by the sphere. These propagating plane waves will radiate to the far field. And we have also some evanescent wave components that we can model. Those evanescent components would die out in the vertical direction as we move away from the sample. So therefore, they would not radiate to the far field. And we mount this matrix that are made of two dictionaries of incident sound field in blue and the reflected dictionary in orange here in the figure. So you would have an incident sound field in blue and a reflected sound field in orange. We use the model and the data to estimate the wave number spectrum that you can see a 2D map here. Don't worry about what does that mean. I'll try to explain in the near future. But we are estimating quantities in a domain that is not spatial anymore, is in wave number domain. So basically, what we are doing is to try to use this kind of model here, that we have the pressure data that we collect, the dictionary and of plane waves, and we have the complex amplitude of these plane waves. And we can write plane waves very simply as this exponential function. And so each column here contains one plane wave. So we see K1 here. It's a three-dimensional vector that says what is my wave number in three directions. And across the lines of this matrix, we have the receiver positions. So we have microphone 1, microphone 2, and microphone M. And typically we have much more plane waves than we have microphones. So it's an underdetermined system of equations. And we have this noise term here that helps us to map for inconsistencies and noise presence in the measurement. This model here is based on statistically optimized near-field acousticography, based on this work of Hout. And basically what we do is that we use the model, but we need, as we have an inverse problem here that is ill-posed and underdetermined, it requires a regularization. So we basically solving a Tikhonov regularization problem, where we try to minimize the norm of the residual, so what the model predicts minus the data, and we try to keep in check the norm of the solution by this using this regularization parameter. And we can optimize and find an optimal regularization parameter using the L-curve criterion that is reported in the literature as well. And once we have computed the complex amplitude of all those plane waves that we have in our model, we can use this information to reconstruct pressure and particle velocity at the surface of the sample, and then compute the absorption coefficient of the sample. Typically, we would use this information to reconstruct impedance, surface impedance, at a grid of points on the surface of the sample. So from measurements of the microphones, we can actually reconstruct the surface impedance. Well, we have a simulation study to investigate the edge diffraction effects. So I used boundary element methods to simulate several kinds of samples that have different flow resistivities, thicknesses, simulating low absorbent samples or high absorbent samples, and different sizes of samples and so on. So we can see how the measurement method behaves for different sizes of sample. And here is a result for the wave number spectrum that I explained in the figure before. So we have here on the lines here, we see samples of different sizes. So this is a 30 centimeter sample, 60 centimeter sample, and 1 meter sample. And what we can see here is the reflected part of the wave number spectrum. So what we see is always a blob in the middle. This little red part here is because we have a specular reflection. So we have the incident sound field, and then we have the specular reflection, and that red circle is representing exactly the reflection that goes towards the far field. This gray circle here separates propagating plane waves and evanescent plane waves. So anything outside this circle is evanescent waves and will die out in the near field. And what we observe is that when we measure, we observe this distinct specular reflection inside the radiation circle then, and we observe several evanescent components that are associated with edge diffraction. We say that they are associated with this, the finiteness of the sample, because we do not observe them when we measure an infinite sample or when we analyze the theoretical solution. It's not present, but when we measure the finite observer, we can see that there's this evanescent components. And the evanescent components, their strength is smaller for larger samples. So the larger the sample gets, these evanescent components tend to decrease in strength and magnitude, and they spread less across the kx and ky here. And also their location on this map is frequency dependent and angle dependent as well. So if we move the sound source around the sample, we can observe that these components change in position, and that is associated with plane waves traveling across the surface of the sample, which is very interesting phenomena to observe in the simulation. And when we reconstruct the surface impedance and recover the absorption coefficient, we observe that the methodology is very stable to the sample size effect. So essentially, what you are seeing in this figure is we have in black dashed line what we would like to predict as an infinite absorber. This is what we would like to get to. Here in the gray, you see a simulation of the measurement of an infinite absorber. And then in the colors, we see different sample sizes being represented. And we can see that we get to very similar results to the infinite sample, which is very nice. And it's more difficult to get to this result when the sample is lower in absorption. So that happens because we're trying to reconstruct pressure and particle velocity And because of effects of noise, you would have a deviation in the particle velocity reconstruction, and therefore our estimation of absorption coefficient gets less precise. But anyway, every sample size returns us sort of the same result, which is kind of interesting to observe. The method is kind of robust to the sample size effect, which is interesting. And so to finalize, I want to just give some take-back lessons. In general, we can say that sound absorbers are used everywhere for noise and reverberation control. There are different characterization methods, and we need to understand their assumptions, advantages, and disadvantages. On the materials, the basic absorption mechanisms of materials are viscous and thermal losses in porous materials, and absorption tends to increase with frequency and thickness. And for the resonant absorbers, we have absorption that peaks around the resonance, and usually you have a multi-layered system as well. On the standardized methods, the impedance tube is standardized, mathematically simple. We can retrieve impedance absorption coefficient under normal incidence, 0-degree incidence. And for the reverberation room, we have a standardized method as well, mathematically simple, and we can only retrieve absorption coefficient under diffuse sound field. And on the in-situ methods, they're mostly non-standardized. I think we have one that is standardized to measure ground surfaces. It's possible to retrieve impedance and absorption as a function of incidence angle, but the methods can be mathematically much more complex. And also we have this now investigation. The group at DTU has been publishing this for the last 5 years or so, using array methods, can offer substantial information on acoustical phenomena. And it's very interesting as a new tool to assess absorption of samples, and maybe in the future as well, scattering of rough surfaces and diffusers. So that was about it that I have for today. Thank you very much for this invitation. I was very honored and thrilled to give you this presentation. I hope it was interesting. And many thanks also to the group at DTU Electro, especially to Efren. It's been 1.5 years of cooperation. And to colleagues there, such as Melanie, Antoine, Samuel, Manuel, and to my colleagues here, Will, Paulo, Vivi, Roberto, Dinara, and Christian, and students working in such projects as well here at our university. Thank you very much.